Okay, let's go. Right, so this is like SSRP and it's just basically a revision. And these are my notes. Okay, so let's just start. First, you got the conventions. A signal x is a sequence of values x sub n. N is used to represent the total number of samples. Indexing usually happens from 0 to n minus 1 in DSP time domain. Okay, we all know all of this. Okay, so just move on. Then you got noise in the system, which, well, let's be honest, we are not dealing with that in any case in this course. This was like some extra reading that I did. Never mind. Conventions, continuous signals use parentheses, while discrete signals use square brackets. Although my professor is a bitch, he doesn't use square brackets. Instead, he uses like parentheses for both. I don't know why he does that, but well, anyway. Then you got linearity. So LSI and LTI. LSI refers to linear shift invariant and LTI linear time invariant, although they are basically the same thing. So what basically I mean by shift invariance is, let's say you have a signal x sub n and then you find a signal like, okay, so when you input x sub n to some system, like it gives you y sub n as the output. Now if you like input x sub n minus 1 into the same system, or let's just say x sub n minus s, so it's just shifted basically, and if you put that, then this should just give you y of n minus 1, sorry, n minus s. That's what shift invariance means. Same thing for time as well, but you just got like t minus t naught or something like that. Never mind. So that's shift invariance. Then you got like linearity, of course. If you like put two signals, then the outputs get summed basically. If you increase one signal by some factor, the output increases by the same factor. So that's like additiveness and homogeneity. Those combined become linearity and whatever. Then you got a bunch of decompositions. So first, the even odd decomposition, which let's just say we're not going to talk about this at all because I'm not interested in it right now. Fourier analysis. Let's just start. So first you got the Fourier series, and I'll not look at any formula. I'll just like go straight into it and later on see if this is correct. So let's just say you got a signal x of t, and it's like we know what it is in a time period, so like 0 to t, or in fact any interval which is of length capital T, where t is a period of the signal. Then what we can say is you can approximate this function x sub t in that like interval using this summation. So it's a summation of c sub I, which are like coefficients of something. This something is this complex exponential. It's just like e power j omega t, so it's omega I sub t in fact. But omega I is the ith frequency, which is like the ith multiple of the base angular frequency, which is like 2 pi by capital T. That's the base frequency, that times of I. So by the way, I is not the imaginary unit anymore, it's j instead, which is the imaginary unit. I know, weird convention, but electrical engineers do that in any case. So there's this like what was I doing, right, this times t, of course. So that's how you would express it, and it's like from I goes to, it's supposed to be negative infinity all the way till infinity. So like you got all kinds of frequencies, and yes, kindergartner, like those professors who think that BTech people are kindergarten kids, well, they'll write like sine series and cosine series and all of that. I'm not interested in any of it. I'm just gonna go to complex numbers straight up. So that's your Fourier series. Now how do you find these CI coefficients? So what you do is just like you multiply by e power negative j 2 pi by t I t for some certain I. So you multiply by that particular negative complex exponential of negative frequency, whatever. You multiply by that on both left hand side and right hand side, and then you integrate in the interval 0 to t. So you just got like 0 to t integration of x of t, so x of t, and then you got e power negative j 2 pi by t I t. That's equal to, so all the other frequencies will just get like cancelled. This is like done in depth in most derivations, and like even 3 blue 1 brown has a video on, and never mind, just watch it. So what do you get? Just get like ci comes out, and then you got this integration from 0 to t of, this is 1, so 1 dt, which is just capital T, no doubt. So what do you got? You got like ci is just 1 by t, and then all of this stuff, right. So this thing I call as the Fourier transform defined on the interval from 0 to t, or I should say the t length interval. It's not the Fourier transform the way people see it, but well, anyway, let's move on. So that's Fourier series. Let's go to CTFT for aperiodic signals. Of course, we can like just extend the Fourier series to it. So you had like x of T is equal to the summation of, well, you got like 1 upon T over there, summation of this integral thing, which let's just call as x omega. Okay, no, let's actually go for it the correct way. It's like 0 to T, and then you got x of T e power negative, just call it omega I T. Alright, cool. Yeah, right, and this stuff times e power, okay, I should squeeze it, this stuff times e power j omega I T. I guess, yeah, there's supposed to be a dt involved in there, right? So then what you can do is, of course, just like think of 2 pi upon T as t omega. So then you have to, of course, have a 1 upon 2 pi. So then this just becomes like 1 upon 2 pi. This summation just becomes an integration. And remember, this summation is going from like all the, like from negative infinity all the way till infinity. So you can like think of it going from negative infinity to infinity over here as well. And then this whole thing, this just becomes like integration from 0 to infinity. But in reality, what we should do is actually go from negative infinity to infinity, because when we say like our interval is t length, we are not just saying like our interval is t length and starting from 0. It could be any interval really. So we could also have this interval t by 2 and negative t by 2, and this is the interval that I usually take to like get this thing. So yeah, it actually goes from negative infinity to infinity, and I get it. It's like weird, why is this even happening, but there's like good reasons for this. So it has to be in fact from negative infinity to infinity. You can't do it from just 0 to infinity. You just get half the integral sometimes. So yeah, I mean in cases like it's even function or something, but you get it, right? So it's just going from negative infinity to infinity of this shit. It's just x of t, and then you got e power negative whatever this is. So instead of omega, I'll just write omega directly. So like omega t and then dt, and by omega I actually should just mean whatever omega you have over here, right? And then this thing d omega. So it's like it's a double integral, and that's how you approximate x of t. Now it's not an approximation anymore, it's just like writing it a little differently, but yeah, that's pretty much. Oh, okay, I missed something. I missed this thing, e power j omega t. Right, so this little bitch, it's called the Fourier transform. It's called x of omega a lot of times. So what we should in fact be writing is like 1 upon 2 pi integration from negative infinity to infinity of x of omega, and then you got e power of j omega t and then d omega. That's like the inverse Fourier transform. In any case, let's move on. In fact, these equations work for aperiodic, and I mean, of course, these work for aperiodic signals, because aperiodic signals basically have the time approaching infinity, so that you get like d omega and stuff like this. Okay, cool. Now there's a little problem with this. Although it's like only for aperiodic signals, it's actually used for periodic signals as well. So when you use it for a periodic signal, let's say for example e power j omega t, where omega is some number, then you would get some kind of weird result, and the weird result is that you just have like it being 0 everywhere. And I shouldn't even say it's 0, it's more like not defined or something like that. At least the Fourier coefficient would be 0, supposing t approaches infinity, but yeah, more or less the Fourier transform is like not defined, and then when you have like it matching exactly, so for omega equal to this w thing that I've written, you just get infinity. So that's weird, I think, but in that case you can just do it from the basics and just say, okay, it's like as t approaches infinity of the Fourier series. So then it's basically the Dirac delta function. In any case, just move on. So yeah, this is like what you should get. So just check it. It's like 1 by 2 pi that cancels with this 2 pi, and then the Dirac delta function integrated over omega, not f, over omega. That will just give us 1. Yeah, move on. So that's the CTFT of aperiodic signals. Then you got a DTFT. So DTFT is basically like the CTFT, just approximated. Yeah, I mean that's actually it. People hype it up so much. I don't know why. So remember, your CTFT was given as x of omega is equal to is like, okay, in fact, you know what, let's not even go for the full CTFT, let's just go for the t length CTFT thing. So the Fourier coefficient was given as like 1 upon capital T and stuff, but like let's forget about it. Just integration from 0 to capital T, this will be using, and then you got x of t e power negative j omega t dt. Right, so that's your, what is it called? Yeah, it's called your T length CT. I'm just gonna call it T length CTFT because I have no better term. Right, so we can like approximate it as a sum of what do we call it? Sum of squares, no, rectangles approximation. So let's say that your sampling frequency is Ts, so you only know some values, like what's x of n Ts for n being an integer, which is like not a lot of information because you want infinite amount of information, which is not comparable to some finite amount. But in any case, you can do a good approximation if your Ts is pretty small. So what you will do is you just like break it as a bunch of rectangles, so you approximate like that, and then you just got x of n Ts, and then e power negative j omega Ts, we'll just have omega Ts n, and then instead of this dt, well, you just forget the dt completely. In essence, your dt would be in fact Ts, isn't that right? So this would be Ts, but what we actually do is like we kind of forget it completely. Right, so this actually is what we call the DTFT, while it should really be like Ts times that for it to make sense, but in any case, we just forget it. Yeah, that's weird. In any case, so as your sampling time approaches 0, of course this just becomes equal to the CTFT, like this expression. But otherwise, this would be basically like this is the DTFT and that times of Ts. Yeah, this is the DTFT, not the complete thing. Just remember that. So what we can say is like DTFT times Ts. That's approximately CTFT. Okay, cool. But then again, like DTFT is for any omega, but really for the Fourier series that we actually want to use, we only need some omega. What kind of omega do you need? You just need multiples of the base angular frequency, which would be something like 2 pi by capital T times some constant k. Sorry, some number k. Right. But another thing is, since we are like sampling and all, might as well write T as NTS, because you got n samples and like Ts of space between each sample, so we write it as NTS. And so instead of defining omega like this, we actually define it like this. Yeah, so it's actually like, so it should be omega sub k. So 2 pi upon n times k. So now it's a pure number, which means you can do like e power whatever stuff involving omega without involving anything like Ts or Fs or anything. So what that basically means is like regardless of your sampling frequency, you can take like the DTFT thing at certain points that you need for the Fourier series, not caring what your sampling time was. And so that eventually leads to DFT, right? So the DFT is, I don't know why people hype these things so much, but yeah, it's basically just a DTFT sampled at some points, that's it. So a DFT is basically the DTFT, but it's denoted as x sub k, where by k you mean the kth integral multiple of the base frequency. This is the base frequency, not quite, you have the 1 upon Ts factor, but this is like Ts times the base frequency and that times of k. Right, so evaluated at that, that's, yeah, the DTFT at that point. Yeah, that's pretty much it. And there's a whole thing called like this Nyquist criteria and shit, which says that your sampling frequency should be bigger than 2 times the maximum frequency and something like that, which also means like your maximum frequency should have always been less than the sampling frequency upon 2. Well, the sampling frequency is basically like 1 upon Ts, and that converted in like angular frequency would be something like 2 pi upon Ts. So it's pretty clear this is basically like n times of the base angular frequency, let's call it omega sub 1. Right, so n times of omega sub 1, that's this thing, and so we want half of that, so this is like that upon 2. So your biggest frequency, omega max, I guess, because angular frequencies, right? Yeah. So your omega max, that should be less than this value. So really, when you are evaluating these like what we call it, like when you're evaluating your DFT from DTFT by taking sampling and all, you only really need to do it for some angular frequencies, right? Some discrete values, only in some interval. the interval being that, well, this should happen. This is what we require, this t sub s, by the way. So if this happens, well, good, otherwise bad. Right, and this of course happens when your k, because you know, like omega is just something like this, there should be omega k. So this happens when your k is less than n by 2, or mod of k is less than n by 2. Yeah, that's the thing. So we really just go from negative n by 2 to n by 2, that's all we need. And then you might say, okay, what about the other frequencies, do we not care about? We can just get that, but then the thing is, those are actually kind of redundant. And you will see why that's redundant when you try, like, actually write out the Fourier series. You'll see, oh yeah, these are in fact redundant, because we are not evaluating the Fourier series for all of the time, we're just doing it for intervals. So yeah, it would in fact be redundant. Okay, now back to it. And like, they're also redundant given by this relation x of k plus n equal to x of k. That's another way to think that, yeah, these are in fact redundant, but that's not the complete truth. You'll have to, like, actually write down the Fourier series and see that, oh, these complex exponentials are exactly the same functions, so why not, like, bunch them together and just use these negative n by 2 to n by 2 frequencies, right, which are in fact exactly n frequencies. Yeah, because even like the n by 2, you can boil it down to negative n by 2, so you really just have to go from negative n by 2 to n by 2 minus 1 inclusive. Let's move on. So that's DFT, and of course you might ask, okay, so there was like inverse of CTFT, isn't there an inverse of DFT as well? Yeah, there is, and it looks a lot like the inverse CTFT. You know, you had like that 1 upon 2 pi shit. Yeah, it's kind of like that. You have like 1 upon n. Yeah, I don't know. Okay, basically the Fourier series, while doing that, what you basically do is like 1 upon capital T and then the so-called Fourier transform over like one period, which at this point is like xkts, and that times the complex exponential thing, and now it's like sampled at n rather than every single point t, right? So it's like at nts, that's what I should say. Yeah, and you just like add all of these up, all these frequencies up to get the approximation. So that's like your x. I shouldn't even say approximation, it is the thing, but well, in any case. Right, what was I doing? Oh yeah, right. So I was explaining how we got this inverse. So it like basically just write capital T as n, so capital N times of ts, like this, and then like things boil down pretty easily. So just get this thing. So the Fourier series terms are basically like 1 upon capital N x sub k, this complex exponential shit, and you just sum these up and you get x of n. Remember, these are, by the way, functions of n. I shouldn't even say functions, sequences of n, that's more like it. In any case, let's move on. So that's like the Fourier transform and its alternatives and like discretized versions. In any case, let's move on. So there's also this other more generalized stuff like the Z transform and the, you know, Laplace transform, but really those are just like Fourier transform. There's nothing new for me to tell in that, except that instead of like j omega, you have complex frequency s for the Laplace transform, and like instead of the complex exponential, you just have like z power negative n, where z is like any complex number, constant complex number, I should say. So that's the Z transform and complex transform. Okay, let's go to the properties. Fourier transform is linear. Yes, that you already know. I'm not even going to go over it. It's like shift in time domain. So suppose your y, what's happening to this pen? So y of n is given by x of n minus s, where s is like some shift. Then what's gonna happen is you just have the dtft is like y of omega is x of what's I going to say? So it's like x of omega, but now you have this extra thing. So it's positive. I guess it was positive. Was it positive? Yeah, it must have been. Like you got minus s involved in there, so you made a plus it, but that's negative. So it's really just negative. So just negative j omega sub k, by the way. Okay, never mind, it's omega, just omega, and then s. And that's more like it. Cool. So that's like the DTFT. Cool. Nice. Yeah. What else was I doing? Okay, right. Also the continuous thing. So x of, suppose y of t is x of t minus t naught, then it's that this is like pretty easy. You can just jump from there to there. So it's like y of omega is, this time it's the CTFT over there. So it's e power, no, it's not supposed to be negative. Why did I write negative? I just said it's supposed to be, okay, this pen is horrible. Oof. Okay, let's just make sure it's positive and not negative. So in the n minus s over there, you put in minus s, you put a plus s to cancel it out, but that's in negative, so now you got negative s out. So no, it's actually negative. It actually is in fact negative. And over here as well, you just have negative j omega t. Okay, that's it. This pen is horrible. It's doing something. Why can't I use it normally? Do I have to press? Yes, I have to press harder, it seems. Okay. So let's just see what actually the thing is. Shift in time. Yeah, it's negative. It's negative. So yeah, 2 pi by n and then k. That thing is what is it called? That thing is omega. And I wrote it like for the DFT thing, it's also the same thing for DTFT. I should have actually written this directly for DTFT and not DFT, but whatever. Okay, the shift in why am I even seeing this? Shift in frequency domain, right? So here's one nice thing. When you're like going from frequency domain to time domain, it's also something similar to like the Fourier transform, except you're not multiplying by negative j omega t, but instead e power plus j omega t, and then there's like some constant stuff thrown in. So you would expect something similar, right? Yeah. So if once again, let's just say that your that you have like y of, so let's just go for DFT first. So it's y of k equal to x of k minus s. Then in that case you will have to say that y of n, so y of n, that's equal to x of n, but you have this positive thing, so e power right, with respect to k, the angular frequency that you should be having is 2 pi by n k, and then you got positives, right? Similar stuff for the CTFT shit. So if you got x of omega equal to, sorry, y of omega, right? Yeah. So you got y of omega equal to x of omega minus omega naught, for example. Then you just have y of t equal to x of t times e power j omega naught t. I guess that's how it should be. Yeah, I'm sure that's the way it should be. Right, it makes sense, right? Because in the integration you got like something e power omega stuff, so this is gonna happen. And even like for what was I going to say? Yeah, so even if these are like DTFTs of some discrete signal, then this would actually just give us yn is equal to xn, and then you got e power j omega naught t. Yeah. So just let's see what's happening. Yes, so positive numbers. That's more like it. Yeah, cool. Okay, let's go for so compression is something I kind of mess up all the time. But this time I won't. I don't promise, but let's try to do it. So suppose you have y of t. So first the continuous one. That's equal to x of. Yeah. So if it's equal to x of at, then you can say that the y of omega thing, that's equal to 1 upon a x of omega upon a. Yeah. And if you have y of n equal to x of an, then y of k, that is basically like just x of n by k by a I kind of wonder what would happen for the DTFT, right? I suppose you would have a similar relationship. Yeah, I mean, since the DFT is basically DFT sampled at points, I suspect it's going to be the same thing. So we just have y of omega equal to x because remember, while doing a DTFT, you were like summing things. You weren't like doing an integration. So you wouldn't have that 1 upon a thing going on. I don't think so. Because over here the thing is like you got this omega upon s, so when you integrate to like get the inverse back, it's like a bit of substitution happening, and so you need a 1 upon a over there for it to work out. Over here you do not need that. I guess that's correct. So this is like x of omega upon a, I suppose. Damn, it feels like I'm... Nah, it's okay, it's okay. Just move on. It's like compression, and then this relation I'm not gonna go through because people haven't taught me that yet. There's sampling, which is complicated shit. I'm not saying that. But yeah, the gist of it is that when you sample, let's just think what happens when you sample. Let's say you have a continuous time signal x of t, which you send into something like an ADC, and that spits out this x of n. What this x of n actually represents is something like what is the value of x of t at t equal to n ts. So this is like all the values of x n ts for integral values of n. And now let's say that you want to construct back this signal. Well, how would you do it? Right, so when you like get x of n, what actually is happening is like you're getting this area of under x sub t for this like ts range, and you are dividing this area by ts, because of course that's what this height should be, right, approximately, and that's a good approximation for xn, I guess. So you want to get back to the continuous domain with the same kind of thing, that in this area, like this area, that's just equal to ts times x sub n, right? So the area in every ts interval is just ts times x sub n. But once again, you do not actually know what the distribution is, so there are two ways to do it. One is like you just form a rectangle, right? So that's called a zero order hold. There's actually three ways, in fact, actually a bunch of ways, but never mind, we'll just talk about three ways. So first is you hold, so that's zero order hold. Then the other thing is like you connect these lines, so that's a linear function is how you approximate. So now you're like dealing with trapeziums rather than rectangles. And the third one is the most fucked up way to do it. That's how I'm gonna describe it. But what we basically do is at every nts you create a spike. You create a spike with area being equal to ts x sub n. Yeah, it's a direct delta function, and you create a bunch of these direct delta functions. So essentially what you're doing is like you're multiplying x of t. Okay, let's actually forget all of that. Essentially what you're doing is you have summation of multiple direct delta functions. So that's like summation of ts x sub n, and then the delta located at nts, right? And it's like from negative infinity to infinity, I don't care. Xn could be not causal or anything. So that's how you get back to the continuous domain. And I know it's bad. It's the shittiest way probably to do it, but it has some very important implications, because when we are doing this, there's a good thing that this new function has. It's that when you integrate this function, or this function times anything, in fact, it basically converts the integration into another summation. Moreover, this function can also be represented as this thing, summation of the negative infinity to infinity. You got ts x of t, because really it doesn't matter. Yeah. So you can also think of this function as being this. but then you can like take this stuff out, so you just got ts x of t, and then this summation from negative infinity to infinity delta t minus nts. And this thing is what people usually call the impulse train, but I won't call that the impulse train, because yeah, I follow my own conventions, right? So instead of that, this times ts is what I'll call the impulse train. So I'll define delta of t, once again a completely made up name, it doesn't have this name in real life. So this is like ts summation from negative infinity to infinity of delta t minus nts. Of course the summation is over small n. Yeah, I should write them down explicitly. So essentially the reconstructed signal, let's just call that x bar of n, sorry, not n, now it's t, x bar of t, that's given by x of t times this delta of t. Now what you should notice is that since it's written like this, that's what x bar of t really is. Taking a CTFT of this thing, you just get like capital X bar of omega, that's equal to so once again, what do you do when you take the CT? You just multiply by e power negative j omega t and then integrate, right? Because of these direct delta functions, we just have to integrate over nts values, right? So you just have this thing, summation of ts xn, and you just got e power so negative is like positive, I guess, no, okay, because it's a delta function, so just take out that value, that's about all it does. So it's just negative j yeah, omega tsn, I guess, right? Am I doing it correctly? I am doing it correctly. So over here omega is supposed to be not a unitless quantity, instead it's the actual angular frequency, so it's something like 2 pi by capital T some shit. Anyway, now notice that this can be written as something like, so if instead you prefer a unitless quantity, so then so then like omega ts is what you can rename to be omega, and this thing would just become like x bar of omega times ts, I guess, and then you will just have this thing ts summation x of n e power negative j omega n. And guess what this thing is? Well, yeah, it's the DTFT. So it's just like x of omega, if you want to call it that, right? Once again, we are like going on thin ice over there. Isn't there like some better naming convention for this? Because x of omega would also represent the CTFT of the original function x of t, but in this case we're talking about the DTFTs. I'm just gonna write it out, right? I'm just gonna write it out. It's the DT. This is weird. It's a DTFT of xn evaluated at omega. Yeah, that's better. Or for this matter, forget about this naming convention completely. I'm just gonna say it's evaluated at omega ts. That's better. Yeah. So it has this nice property that, you know, the CTFT of the reconstructed signal is basically just the DTFT of the sampled signal times ts, of course. Right, now the thing is, if we just knew what this guy is, like, okay, what's the frequency response, I shouldn't even say that, what's the Fourier transform of this guy, then we could use the convolution theorem to, like, let's just say like this has the impulse response of I of omega. Then we could use the convolution theorem and say that, okay, cool, you just have x bar of omega is something like, and by the way, the convolution theorem for like Fourier transforms multiplied together, that's slightly different. So not Fourier transforms, for things multiplied together going to a convolution in the frequency domain, that's slightly different. So over here you would have something like 1 upon 2 pi x of t, sorry, capital X of omega, which is now the CTFT, yes, no more DTFT over here, of the original signal, and that times this this like spectrum thing, convolution actually. So yeah, you're taking convolution of these two. So if you could just somehow get the Fourier transform of this thing, you would be having like direct information in regards to this thing, but you also have like the fact that this thing is equal to TS TTFT of this, so that would like give you some relation between the CTFT and DTFT, which you already have by the way, but yeah, it will like give us more information. So yeah, we'll actually like go to that later, but that's what sampling is about. And like when you will get this relation, you will see that for the DTFT to be kind of the CTFT like thing, it's like it should like represent CTFT in its full essence. For the DTFT to be accurate, you would require that the maximum frequency in the actual like CTFT that be less than the Nyquist frequency, which is basically the sampling frequency by 2. We'll prove that later, but yeah, just deal with it right now. Okay, so that's sampling. When you got the sampling theorem, a proper sampling is one such that we can reconstruct the original signal using the sampled one. Okay, this you already know, this like we just talked about. So this is also called like the Shannon sampling theorem, well really just referred to as Nyquist sampling theorem, but in any case, so for proper sampling, just have the sampling frequency bigger than 2 times the maximum frequency contained in the spectrum. In practice though, we used a different criteria for like proper sampling. So we actually put fmax plus some small like buffer thing. It's called fg, fguard if you want. Oh, and like what happens when you have improper sampling? Well, when this improper sampling, something like this happens. Say your x of omega, which is like the CTFT, is some shit like this. Your what should I call this? Yeah, your DTFT is like the negative n by 2 to n by 2 version, whatever that corresponds to in this like time domain version of the CTFT, but the CTFT is like repeated a bunch of times and then superimposed on itself. So like it's actually the summation of this thing that's what matters. So maybe something like this, and so if this thing is like going beyond a certain point, then we are in trouble because like frequencies that had a relatively small amplitude, well now they somehow match up and like create a bigger amplitude than that should have been. So it does not represent the CTFT in like its full essence. There's like some errors and some problems. So what is this interval that we want our CTFT to be contained in? Well, yeah, it's like this interval. It's negative of fs upon, so I should really just go for the angular frequency. So it's like negative pi fs, and this is pi fs. So you want your angular frequencies to be contained in this thing, which means of course the normal frequencies are supposed to be contained in minus fs by 2 to fs by 2, right? Otherwise weird shit happens, and then your DTFT does not really represent the CTFT, and it's called aliasing, as in frequencies that were actually supposed to represent something else are now representing something else. So like they have aliased themselves as frequencies that were not in the spectrum originally, and that's a problem that people deal with. So that's why these criteria are like so important. But let's like give you a more grounded approach to this thing. So if your sampling frequency is too low, and your spectrum contains frequencies which are like kind of high, then this is the kind of graphs you get. So for example, over here, this is what's happening. You're sampling at intervals which are containing a full period of the wave, and so you're not able to represent the wave by your samples at all. Instead, it's representing some other thing completely. So yeah, right. And this is something that was like taught to me a long time ago in electrical lab, and at that time I didn't understand any bit of it. What's aliasing? Why do we need like half the maximum frequency? Okay, 2 times the maximum frequency, and what's going on? But now I kind of do. Okay, this is not important. This is the digital analog converter. So as I told you, we can just like do the impulse kind of thing to reconstruct our signal, but a more sensible approach would be to hold the signal value and like let that do the job. So over there the area is still supposed to be ts times x sub n, but now since you're holding for ts long, your height is going to be x sub n. So that's much more sensible, I suppose. And so for a zeroth order hole, you still get the same spectrum, right? Your DTFT and CTFT still match, except they don't actually match, except that the spectrum you were getting like by the impulse train thing, you have that multiplied by this function. It's sinc of pi f upon f sub s, and if you want to write it in of omega, it will be something like the sinc of pi omega upon omega subsampling, which is 2 pi fs. So this is like upon 2 fs, yeah, something like that. I guess, right? Am I doing it correctly? I guess I am, yeah. So that's h of f, which you have to multiply this with in order to get the actual spectrum. Never mind, just keep on going. That's DAC. Then you got the anti-alias filter, which is a filter that, like, okay, so suppose your original okay, what was I going to say? Yeah, so your original signal x of t, it had this very bad like spread out, I'm just gonna clean some stuff up. It had this very bad and spread out kind of frequency domain, like spectrum, and you don't want aliasing to happen, but you know it's gonna happen because it has a very spread out spectrum. What you can do is like chop it off everywhere where it's like outside of the interval, and of course the chopping out will be kind of smooth, so you will get something like this. Yeah, so you won't get like full recovery, but it's good enough. So in the sense, what you have done is like you have multiplied x of t by some function like this, and this function is called a band pass filter. In our case, since it's centered at 0, it's a low pass filter. But yeah, in this context it's called the anti-alias filter because it like avoids aliasing, right? And so the full process is something like this. You have some x of t, you pass it through an anti-alias filter to like chop off the frequencies above the frequencies that you can actually implement, and then you pass it to an analog to digital converter, which like converts your x of t into x of n. Then you do some kind of digital processing, I don't know what you're doing, but you get some output signal yn. So now yn has to be converted to analog once again. So you do that by the 0th order hold, for example, and then you once again pass to an analog filter, which is like a reconstruction filter or something. I actually don't know about that much. Then you get like the final output. So yeah. Okay, let's go straight into the meaty topics. I talked about impulses, right? What is an impulse in a discrete signal though? Like for a continuous signal, you know it's just a direct delta function. For a discrete signal, an impulse is something that's 1 at 0 and 0 everywhere else. Or if you like shifted impulses, it's 1 at some certain n and 0 everywhere else. An impulse response is, well, the response of a system to the impulse. Pretty descriptive, right? So if your like system spits out y of n given xn, then given delta n, it will spit out hn. Easy as that. And that's actually all you need. This is also defined for continuous systems the same way. If you feed it with like delta t, it will spit out ht. Okay, h of the h, I guess, yeah. Then impulse response and general output. So once again, you can think of x of n being like decomposed into a bunch of impulses of varying magnitudes, and since your system is linear and shift invariant, you can just like get the impulse responses to those impulses and just like add these up, you know, And so the process is written over there. I'm not going to go over it. The same thing can be done in continuous in like continuous systems as well. So all in all, what you have is like for an LSI or an LTI, just have y equal to x star h. Well, this is like the convolution. So the convolution, it's pretty descriptive, like notes I have written, so I'm not going to explain that, but yeah. So for discrete signals, the convolution is like something summation I equal to negative infinity to infinity of x sub n h of, sorry, it should be I over there, I h of n minus I or something like that, or the opposite, x of n minus I and h of I or something like that. Right, this is like our output signal. So this operation that we are doing on x and h, that's called x star h for discrete signals. For continuous signals, you have like y of t is equal to integration from negative infinity to infinity, I should say tau, some dummy variable, and you got like x of t minus tau and then h of tau, d tau. Right, so this once again operation is called like x star h, although now in the continuous case. Let's go. Well, that's the general thing. Okay. So since we are like talked about convolution a bit, let's go in deep about convolution. So for discrete signals, I just defined it. Actually, I'm not gonna go over it. For I did it as well. All right. Properties: commutativity, pretty self-explanatory. Okay. Associativity, and then there's like distributivity, pretty obvious. And then for any signal x, discrete or continuous, we have that x starred with a delta function is x itself, and you can see that because like I don't want to do anything, but yeah, let's just say that you had a function like this. Okay, what is happening to it? Right, what was I doing? Yeah, so since it's commutative, just start like x of tau, and then you got delta of t minus tau, I suppose. Integration of that, and then you got d tau over there, something like that, I guess. Never mind. You can just start with like x of t minus tau, because that's easier to deal with rather than a delta function being flipped around and stuff. So x of t minus tau, what does that actually represent though? Say this is like your x of t, then x of tau, for example, then x of minus tau, that would be like just this thing flipped, right? Yeah. And what about x of t minus tau? Well, that would be this thing flipped and like shifted basically. So all in all, it's just some like signal, sorry, some function. Well, that times of the delta function at tau. So like delta of tau, that's basically like at 0 you just have a spike, everywhere else is just gone, so you multiply it with that, you just pick up whatever is the value of this new function that you have, x of t minus tau, at tau equal to 0, and you like just spike it up, and that's like delta t times this. So really you just have to put tau equal to 0, so you just get like x of t times delta of tau. This is like also a valid representation of the same function. So they just have to like integrate this thing from negative infinity to infinity, and that's pretty easy, right? You know that the integration of the delta function is just 1, so this is like of course x of t. So for the continuous case it's pretty easy. For the discrete case it's even more easy, which like it's a bit too easy. I'm not gonna go into it. So yeah, that's the way you do convolution. In general, if you're like dealing with signals like xn and that's convoluted with delta n minus s, so it's shifted at s, then you would actually just get x of n minus s. Yeah, this happens. Okay, let's go to the next thing. So you want convolution of periodic signals. Take an infinitely long signal defined over all into fine. So this is like circular convolution basically, we're getting to that. So once again, for periodic signals, you can't actually like do convolution because extended over like negative infinity to infinity. So instead of thinking of the periodic signal being extended from negative infinity to infinity, you think of them being contained in a period. Basically, you just think of what's happening in one period and then think, okay, that period is actually extended throughout infinity. Cool. So let's just say that um, what was I gonna do? Right. Let's just say that y of n, that's actually like a period of the full signal, and x of n is like some random n length sequence, right? Which you think of as a signal, of course. Then the convolution between x and y, that is of course like, I mean, the y full thing, that's of course like periodic, right? um yeah, that's like periodic signal by default, because a convolution is basically like you flip and shift and like multiply and add. It's hard to explain it in words, isn't it? But yeah, all in all you have to do is like just think of what's happening to one period of the convolution that you're getting, and then it's pretty easy, right? And it's pretty easy. You just get like the circular convolution. That's like the sequence that represents one period of the convoluted signal. Okay, cool. So yeah, actually I'm not going to go into this. All in all, I'm just going to deal with the circular convolution. Circular convolution is defined like this. So usually when you do linear convolution, like for discrete cases, say you had a and b length sequences, then your convoluted signal will have length of a plus b minus 1. When I say length, I mean the n values for which, like, or the range of n values for which your signal is not 0. That's the length of a signal. So yeah, that's circular convolution. Then there's convolution theorem for discrete signals. So what we have is like, suppose z of n is x, and then circular convolution y of n, then that's the same thing as saying that zk, which is the dft of zn, that is equal to the dft of x times the dft of y. So once again, DFT and inverse DFT exist, right? Like DFT is a bijective operation between signals, right? And that is like a big hint in trying to prove the reverse implication. Well, in any case, just move on. Yeah. So now, this is also this is also doable from the frequency domain to the time domain, although it's not talked about that much. But during that, you have to, like, while proving this happens, you need to think of Zn, the time domain thing, as being the DFT of the frequency domain thing, like Zk, albeit a factor of 1 upon capital N. So what you should actually be saying is like nz of n is basically the DFT of z of k. Yeah, and that's for all three signals, by the way. So once again, like, applying the initial convolution theorem that you had, the convolution of zk, which is this thing, that's equal to the convolution of xk times the convolution of yk. So no wonder that zn equal to capital N times x of n y of n. So you can't just say like z of n equal to x of n y of n. You have to say x of n equal to capital N times x of n y of n. So it's slightly different, alright, going from the frequency to time domain. Alright, then you have like continuous cases, like convolution theorem for continuous signals. Yeah, so once again you have the normal convolution. It should really just be omega over there, not s. The reason is because it's hard to define the convolution in the s plane. Although you could completely do it, like you could really just do it that, if x of t is x star y of t, then z of s equal to x of s times y of s. It's completely valid, but let's just say it's a harder proof, right? And for the first by implication, okay, I have actually done it with S, and I have done it weirdly actually. Hey, so apparently I did it correctly. So I could in fact replace this completely with S over there. Huh. It just that the reverse thing I cannot do, right? Can I actually like do the reverse thing? No, I can't. Because once again you run into the same problem that x star omega, sorry, x star y of S. That's a hard thing. So Fourier transforms these, and let's just say like Laplace transforms of these or something. Okay, let's just say the Laplace transforms, because with the Laplace transform you can even deal with Fourier transforms. Yeah, okay. Happens. So now it should be S instead of omega everywhere. Sorry, I'm editing in front of you people while it should have been done prior to that, but doesn't matter, right? So over here, instead of saying instead of saying like z of omega, we have to say z of j omega, because S was defined as sigma plus j omega, not not like the way we deal with in Fourier transform. So yeah. So yeah, this is the better thing to say. Right. So the first by implication is actually like doable because it's just an integration in time. The second is kind of hard, but I'm sure you can like do it. Yeah. It's once again like doing the same thing, that the inverse Fourier transform is basically a Fourier transform but with 1 upon 2 pi. So you can like once again just apply the convolution 1 upon 2 pi, and instead of t you are putting minus t or something like that. Alright, cool. Frequency response. Right, that's a big portion of this thing. So first let's just go through some definitions. A causal signal is basically a signal that doesn't exist for negative n values, as in for negative n it's 0. So that's out of the way. A difference equation is basically like an equation that models a system. In discrete cases it's basically a recursion, right? So for example, you would have something like this: y of n equal to h0 xn h1 xn minus 1 and so on till x0, right? So we can think of it as like x star of h n, right? And h might not even go all the way till n. It would just probably stop at hk, for example. But then you can just think of the further values being all 0. So this is still gonna work. Right. So that's like the simpler case. This is the finite. It is like, how do I say this? Yeah, so this is a finite impulse response systems difference equation, right? Because of course when you put in the impulse for n length you will have y being something, but after that like it has completely passed through the system. So yeah, at that point it's like non-existent. Like there's nothing that you're putting in. You're putting in 0 0 0 0 0, xn is 0, xn minus 1 is 0, everything is 0. So then yn is 0 as well continuously. So you have finite impulse response. Pretty easy, right? Yeah. Well, h of n is actually the impulse response that you're talking about. In any case, let's move on. But it could also be a recursion in case of a general LSI system. For example, you would have something like this: y of n is x of n plus y of n minus 1. Well, you actually wouldn't have this for a general LSI. It's not implementable easily, but in any case, for a general LSI system you have recursions. Like you also involve terms of y on the right hand side. So in general what you can say is like h1 star y of n equal to h2 star x of n, and then like taking the what do we call it, like the z transform on each side, and then using the convolution theorem, what I can kind of say is that h1 of z, capital H1, and then y of z that's equal to h2 of z and then x of z. This you can say at any like given instant, and then you can simply say like, okay, that means this is gonna happen, right? Now if you can somehow represent this as a polynomial in z power -1, what that would mean is like you've basically taken the z transform of an infinitely long sequence, right? um, yeah, so if you can kind of represent it as a power series, and that would that is basically like an infinite impulse response system. And then there like lies this question of stability and all that, which we'll talk about later. But yeah, so that's the difference equation for discrete systems. For continuous systems, instead of the difference equation, you have something different. You have a differential equation. So like, yeah, you still have to deal with this shit. It's pretty easy, right? Difference to differential, not much of a difference. that was ironic. Anyway, so that's a difference equation. Then you got frequency response. So basically, it's like you put in e power j omega n as your input, where you get e power j omega n times h of omega as your output. But h of omega is this thing. It's like the frequency response. It's the DTFT of the impulse response, basically. And the impulse response might be infinite, alright? It might be infinite, but it could be that the frequency response is still just like a normal, like rational function in omega or something. Not exactly a rational function omega, but you know, some function of omega which is explicitly writable. You don't have to use like power series or other shit to do it. That's completely possible, by the way. Right. Oh yeah, okay, there's also this important thing that for LSI and LTI systems, you cannot have new frequencies. Like, no matter what frequency you put in, you just get like h of omega, which is some complex number, doesn't depend on omega that much, right? It's not a function of omega, it's the function evaluated at omega. So that value, the complex number, that times e power j omega n, which is a function of n, right? Yeah, so that's y of n, which is a function of n. So all in all, your frequency does not change. You still have something like e power j omega n, just that times some complex number. That's what it's implying. So like, if somehow your system was giving you new frequencies, that means you're in trouble. Either you're in trouble or you have aliasing going on somewhere. Yeah, you can say like either the system is not linear shift invariant, or there's like aliasing happening. Cool. And for continuous signals, there's like no concept of aliasing, so yeah, you just have like, this is not linear shift in linear time invariant. Okay, cool. That's frequency response. There's also like something similar to the frequency response, but you know, response to a decaying harmonic. So over there you had like the DTFT of h of n. In this case, you have the z transform of h of n. So like, given an input z power n, your output would just be z power n h of z, right? For some LSI system. Then there's this thing called a group delay. So you know that you can have like a DTFT, right? So that DTFT tells you what to do for a certain frequency, what to multiply it with. Well, whatever you multiply it with is a complex number, so it has some magnitude as well as like some phase. So how does that phase change with different omega values? That is called the group delay. So instead of defining it as like d phi by d omega, you're defining it as negative d phi by omega by d omega. I don't know why. Probably it has to do with the fact that a Gaussian has its Fourier transform, sorry, the DTF. I shouldn't say the DTFT. Yeah, I should just say like the Fourier transform. The Gaussian has its Fourier transform being a Gaussian once again. So it has to do with that most probably. I think so. Yeah, this we already dealt with. Okay, cool. So then there's the transfer function. I mean, since we talked so much about like this stuff, this Z transform upon that. This is called the transfer function, by the way, which is like it tells us, and we already dealt with this, right? Yeah, we already dealt with this. The Z transform of the impulse response, that's the transfer function, because you have like x of n times h of z, that's equal to y of n. But then again, like y of n as in it gives you one frequency. So how do I even say this? Yeah, like given in an amplitude and like a z, you can get an amplitude and z out. So when we say y of z, we are referring to the amplitude. X of z, it's the amplitude. So like you can actually write y of z, z power n equal to h of z, and then you got x of z, z power n. That's kind of better to think about it like that. Yeah, that's actually a better way to think about it. So of course you can cancel these z power n terms and you just have this, because it's happening for every z value. You can just say, oh well, these functions must be such that this happens. Functions in z, of course. And so this is called a transfer function. H of z is just y of z upon x of z. And of course it's the z transform of the impulse response, which might be infinite, but you still get a rational function in z for some reason. Well, actually not for some reason, you do get a rational function in that, because of the way we have implemented the system. The better question to ask would be, when do you get an infinite impulse response given an h of z, right? And so that is something that's like related to stability of a linear system. But first of all, you get an impulse response which is infinitely extended, like infinite impulse response, when you don't have an FIR system. That is, you have like a recursion kind of theme going on. But then again, you might say, okay, well, you get infinite impulse response when you have even a single like term like yn minus 1 in your difference equation. But doesn't that impulse response decay over time, or n in this case? So I would say, yeah, it does decay. So you might ask, okay, when does it decay? And so to that, I say whenever the system is stable. And that's actually the way we have defined stability. A system is stable when given an impulse, the system comes back to its original state after some time, or gets pretty close to it. That is to say that an impulse response decays over n. And so for that to happen, there's like a whole derivation of this thing, but all in all, the thing is like an LSI system is stable if and only if it has all the poles, which are basically the roots of the denominator of this thing, of its transfer function inside the unit circle. And similarly, an LTI system is stable if it has, so an LTI also has transfer functions which are once again rationals, so rational functions, but they're rational functions in S instead of Z. So you have h of s equal to y of s upon x of s for a continuous system, and this is, by the way, a rational function in S, which is once again the Laplace transform of the impulse response. And the system is, so a continuous LTI system, it's stable if and only if the poles of its transfer function, well, they are on the left side of the complex plane only, right? So there should be no pole on the right side of the complex plane, as in your sigma. So if S is defined as sigma plus j omega, your sigma should necessarily be less than 0 for every pole. Alright, so that is stability for linear system. I talked about pole and zero diagram. So I talked about poles and zeros, right? Well, so we have to go into poles and zero diagrams at this point. So the graphing of poles and zeros on the Argand plane, or the complex plane, that creates something called the pole zero diagram, and it's used usually to like figure out the impulse response. It's like magnitude changes and all of that shit, which I actually kind of don't understand that well. Like, why do they even draw pole zero diagrams? They could just list out the poles and zeros and that's it. I suppose it's more like it's like they have to draw a 3D plot in order for the diagram to even make any sense actually. And so they skip the whole thing and like just draw where are the poles and where are the zeros or something like that. Okay, then there's this whole thing about region of convergence, which I don't like the way it's being taught to me, but yeah, I'll just go through it. So remember the way we were like defining the z transform for any signal h of n? We can say that h of z is this thing, right? I kind of skipped this definition, right? But in any case, I hope you can just learn it on your own. So this simply means that x of z, well, this could potentially be an infinite power series in z inverse, right? The region of convergence is, well, the region, the radius, I guess, no, yeah, the region is a better word. The region of convergence is like the set of all z like such that this power series actually converges to a value rather than like oscillating back and forth or going to infinity or something like that. Particularly when the power series converges to a supposedly rational function in z inverse for, you know, LSI and LTI systems. LTI systems don't have like z, so for LSI systems it should like go to a rational function in z inverse or a rational function in z with some properties. If that happens, you can say like, okay, cool, this was in the region of convergence. Right, so when your like rational function is, so when your h of z is a rational function, you can like just, you know, rewrite it through partial fraction decomposition as this sum, and then explode these single terms as power series of z inverse, and then say, okay, these power series should converge as well. And I kind of don't have a proof for this, but I just trust the sources that I got on the internet. So I'll say, okay, so what should happen is that for every pole, you just have di z inverse is less than 1 for any z in the region of convergence. And so like the region of convergence is basically defined as the magnitude of z being bigger than the magnitude of the pole. So basically like the magnitude of z has to be bigger than the highest magnitude of the pole, and that's the region of convergence. And this is like particularly the thing for causal systems. For anti-causal systems, which like extend over negative values of n as well, things are a little messed up. So over there you actually have to be like very careful how you define that region of convergence. You have to do it like from the ground up, starting from the z transform of the impulse response. Really. Okay, this I already did. Oh, also like there's this whole thing that IR, like infinite impulse response systems, are unstable, or like FIR systems are always stable. Well, FIR systems are always stable, but it's not like IIR systems are unstable all the time. They are unstable sometimes. So yeah, just keep that in mind. Some professors might get too emotional over this stuff. Who knows? Then there's a bunch of Fourier transforms that are worth memorizing. And so delta function, you already know, like the Fourier transform delta function is pretty easy to figure out because of the way that delta functions are defined. It just picks up the value at certain things. So, but then again, what do you expect? Like, what's the Fourier transform for delta function? You just have x of omega equal to the integration of delta of t e power negative j omega t dt from negative infinity to infinity. Of course, this is just going to be like, you know, it picks up the value at 0. So this is just, what's this guy's value at 0? At 1, of course. So it's just that. And what if it's like shifted? So instead of delta of t, you have t minus t naught. In that case, it like picks up the value at t naught. So this is just e power negative j omega t naught. So it's pretty easy to figure this out. Then you have a Fourier transform of a box. Kinda hard, not gonna lie. So what's a box, by the way? what I mean by a box is something like this. It's 1 throughout, and it's 1 throughout in this interval, negative a to a. Everywhere else is like 0. So that's your x of t, by the way. In continuous case, it's this thing. And you want to get the Fourier transform of a box. It's not that hard actually. You just have to do like integration of this thing from negative a to a. It's 1 basically, so just e power negative j omega t dt. That's it, in fact. So just integrate it. What do you get? You just get like upon negative j omega e power negative j omega t from negative a to a. So it's like that negative can just like, actually, you know what, just put that negative j over there. Whatever, just put this. Now it's gonna be like from a to negative a. So put negative a, you just get like e power j omega a, and then minus e power negative j omega a, and that upon j omega. You can see that it's like 2 sine of j, so 2 sine of omega a times j, of course. So then this is like, yeah, I guess it's just 2 sine of omega a upon omega. That's what you got, 2 sine of omega a upon omega. And I suppose that is in fact what we got. So just see box continuous. Yeah, that is the thing. Function is the Fourier transform 2 sine of a omega upon omega. Pretty easy, right? Okay, what happens if like you shift this a bit? So if you know, instead of this being set at 0, it's like at mu for some reason, you can just use the shift property of Fourier transform and say, okay, it's gonna be this same thing except multiplied by e power, you know, negative j mu omega something. Yeah, why this is like x of omega, right? Function of omega, just saying. Cool. So that's easy. Let's go to the discrete case. It's slightly harder. So the general discrete case is that, once again, that's just the way it's defined, but now it's going from minus m to m minus 1, and you have like x of n equal to 1. So to get that, you can do like the sum of sine and sum of cosine things, and it's gonna be pretty easy to do. So the sum of sine thing is like sine of n d by 2. In this case, the n is, you're going from here to here, so it's something like, how many do you have? 2m minus 1, I guess. Yeah, no, okay, not minus 1, because you also have 0, so it starts off at 0, so it's like exactly 2m in fact. So you got 2m, so n, and then you got d by 2. So what's your d by 2? D is the base frequency, which is 2 pi upon n. So n is like the actual full interval, and this is supposed to be periodic, by the way. So this is like the thing, and that upon 2 is just pi upon n. Yeah, seems about right. So upon sine of d by 2, so once again just pi upon n, I guess. Oh no, pi k upon n, remember, because k times of that, right? Yeah, you don't want the base frequency, you want the changes in omega. Sure, like x sub k to x sub k plus 1, the amount of change you have in omega is, it's like 2 pi k upon n. Cool. And then you have this cosine of a plus l by 2, sine of a plus, what is a plus l by 2 first of all? It's like this plus that, which is, so it's something like this. What the hell, how do I even say this? Yeah, so yeah, you have to multiply by e power negative j omega t, right? Okay, negative j 2 pi upon n k and that shit, and then sum it over n. So when you're like doing that, essentially what you're doing is just cosine of 2 pi upon n k times n, and then minus j sine of all of this stuff, the same thing over here as well, right? This is what you're summing up, isn't it? So this summed up, it's like sine of n d by 2 upon sine of t by 2 cosine of a plus l by 2, and then like this summed up, you just have that minus j in the front, right? So once again, what's a plus l by 2? It's just minus 1 over there. So yeah, minus 1 times this stuff and that upon 2, so you got pi k upon n. So you have like cosine of pi k upon n, I guess. And then you got minus j sine of pi k upon n. The same logic. Well, this is like e power negative j pi k upon n, so you can understand. I guess, yeah, just e power negative j pi k upon n. And so that's the Fourier transform of a box function. Once again, you get the same thing shifted by some mu thing, and the corresponding shift would be there in your Fourier transform in like e power stuff. Okay, so that's the Fourier transform. What about the inverse Fourier transform? Once again, the inverse Fourier transform is just the Fourier transform, at least for this discrete case completely, except you have a 1 upon 2 pi factor, sorry, 1 upon n factor. So it's really just 1 upon n, and then you once again have sine of nd by 2. And the weird thing is, like, now it's like d omega, so the change in omega, wait, is that a thing? Yeah, right, the change in, oh, so in the previous case it was like between two consecutive n values, how much did omega change? Now it's like between two consecutive k values, how much did omega change? So now it's like 2 pi n upon n. You get it, right? So it's like n, what's n by the way? Once again, just 2m. If it's going from minus m to m plus 1. Yeah. So you got 2m, and then this is upon 2, so it's like pi n upon sine of pi n upon n. And you would have the same stuff, but now it's not negative, so like e power negative j stuff, it's e power positive j stuff. So once again, like the cosine series, sine series stuff, combine e power j, so e power j pi n upon n. That's what happens for the discrete case, I guess. Let's just see if this is the thing. Yeah, more or less. I see, okay, it's negative over there instead. Oh yeah, okay, there was negative 1, right? It's from negative m to m minus 1, so that's negative 1. In an initial case, it was, okay. In an initial case, for the forward Fourier transform, I actually like wrote negative. It should have been negative of negative is positive. In this case, it's just negative. I get it. So that's what Bn is for the discrete case. For the continuous case, I'm not gonna do it, honestly. I'm tired. So just move on. Fourier transform of any signal that lives in an interval. So when we say it lives in an interval, you can think of it like being a periodic extension, like the way it should be, that multiplied by the box function. So it's almost as if you're taking the it is in fact that you're taking the convolution between the spectrum of the box function times the spectrum and the spectrum of the original signal that you had. So it would give you some weird shit because it's involving sinc function, which is like for all omega and all of that. So yeah, just be aware of that you know, chopping off just so that it lives in an interval, like what we do with the anti-alias filter, it's not exactly a good process when done casually, because it does like create new frequencies. If you're not doing it correctly, like the way it should have been, like with a large enough a value, yeah, then you're gonna be in trouble at that point. Alright, triangular pulse. Okay, so for the discrete case, it's like doable. So once again, just consider the box function, and like let's just take the convolution of the box function with itself. So this is your box function going from negative a to a, it's 1. And when you're starting the convolution, the first index that you want to do it for is like minus 2a, because you got, you know, wait, no, not minus 2a, is it? Yeah, okay, it is minus 2a. So first thing you do it is for minus 2a, so the only overlap you want is like minus a and minus a. That's the only way you can form minus 2a from like two terms. So you just have like minus a and minus a. Right, so it's like 1 and 1, just have Just think about a triangular function. So at minus 2a you just have fun, right? Yeah, just have 1 over there or something. Wait, is that the thing? Am I doing it correctly or what? Oh yeah, it's supposed to be 1 actually. So this is like 1, and then later on it's going to be 2, because it's 2 ways that you can do it, right? Minus 2a minus 1, you can do it as, you know, minus a plus 1 and minus a plus 1 and minus a. So there are like 2 ways to do it. So it's 2 over there, then it's 3, and so on, and then eventually reaches like the maximum point at the center when it's like 0. So for 0 you can start from a and minus a and go till minus a to a. So it's 2a different ways. So this height is going to be 2a. This height is 2a. That's the triangular like thing that you're getting. So it's like 4a wide with 2a height, something like that. So okay, in this case we are doing it for m rather than a. So take it. So okay, it's minus m over there. This is m as well. So it's 2m over there. So xn equal to the convolution of b and b. That's a triangular wave. So you did circular convolution rather than normal convolution. The reason for that is like you're thinking of these being as periods of actual signals. So then this thing here also is like also just a period of an actual signal. So yeah, then in that case x of n, which represents the signal, is like actually a wave at that point. So it's a triangular wave with a pulse centered at n equal to 0 with a peak of 2m and width 4m. Makes perfect sense, I guess. And so now what's the DTFT of this guy, or the DFT of this guy? Well, since it's like the circular convolution of b and b, it's just the bk thing, the DFT of b of n. Well, that thing squared. So it's this. Easy, right? Yeah. Of course, like for this to be the appearance, what should happen is like there should be no aliasing in the convolution. Like, yeah, it's hard to explain. Yeah, it is kind of hard to explain, right? So the condition for that we put is like m is less than n by 4 or something. Yeah, 4m is less than n. If that happens, then this is in fact the appearance that you'll be getting, because you see that 4m, if it occupies more space than n, then like you just have like these periods overlapping with itself. So then we would have something like this. It's hard at that point. So now the linear convolution and circular convolution, they should match. If they don't match, make them match by restricting m to n by 4. Okay, cool. So yeah, this looks nice. It's a triangular pulse for continuous case. It's even easier. And once again, just have like b of omega squared. So yeah. Okay. So Gaussian will just do it like right now. We'll do the simpler version. So we want to integrate e power negative ax square and then e power negative j omega x. Just use t instead. So negative at square and then this thing and then dt, and it's going from negative infinity to infinity. That's your x omega. If your like x of t was e power negative at square, right? The Gaussian. The Gaussian, by the way. Like, yeah. So that would be something like. So you will have to kind of simplify it. So it's e power minus a, and then you got like t minus j omega, so plus actually j omega upon 2a, that thing squared. But remember, you're like having an extra term in there. It's minus omega square upon 4a square times a. So like, okay, minus omega square upon 4a. This term you have to like somehow input there. So you have to like, okay, and this times of minus a, by the way. So this would just be this. So you kind of like put this term for no reason. Wait, did I do it correctly or not? um yeah, okay. So this thing, e power omega square by 4, you have an extra factor in this, so you have to reduce that factor, so it's like e power negative omega square by 4, you have to put that in front. Alright, cool. So just this shit, and it's going from negative infinity to infinity dt. Now here's a weird kind of thing that people do. They say this is actually equal to like square root of pi upon square root of a, which I agree with. I mean, yeah, I kind of understand it, but still it is kind of weird. Don't you agree? Yeah. Well, never mind. What we can do is just multiply by square root of a over there and divide by something like e power negative omega square by 4 upon square root of a. And then it's like square root of at. That's our new thing. So just integrate that. And now it's just turns out to be square root of pi or something. It's like square root of pi upon a e power negative omega square by 4. Makes sense. Yeah, I guess. It's still weird. Okay, so let's see what the actual thing is. So if your x is of this form, then you just get that. So over here you have 1 upon a. Well, don't worry, you can just put 1 upon a over there. So it's like square root of pi, and that's this times a. So I'm getting like a square root of pi over there for some reason. Oh, that's weird. Am I doing it correctly? Okay. This certainly has to be square root of pi, right? Am I missing something? Oh, okay. That's a square over there instead of that. So over here also you just have to put a square, right? And then you got like e power negative a omega. Yeah, right. A omega square. Something's a little messed up, don't you think so? Sure. Okay, what is this? Why is this so messed up? No, it's supposed to be minus omega square upon 4a, not. Okay, right, I get it. And now instead of a you have a square, so of course I get it. It's just a omega upon 2 squared. Yes. And this was square root of pi, of course, and then you have this extra thing for because of the shifting. Yes, understandable. So yeah, this was easy as well. Then finally you go to the impulse train, and there's a whole philosophical issue with that, what's going on. But all in all, the thing is, if you're okay, just delete this. So if you have like x of t is equal to delta t equal to ts summation of delta of t minus n ts, where n is going from negative infinity to infinity, then the Fourier transform is like x of omega equal to, so it's the CTFT, by the way. Yeah, that would just be 2 pi summation of delta of omega minus 2 pi f sub s. Yeah, where okay, this times n, of course. N goes from negative infinity to infinity. Makes sense? Yeah. It's giving you the result. I'm not even going to derive any of it, because it's too much of work, honestly. So these two are not in the exams. I'm not gonna revise that. Then this, oh god, this. But yeah, I'm running a little low on time. I'm just gonna go with the butterfly diagram. There's this thing called a transposition theorem, which says that the butterfly diagram, like for DIT, is exact opposite of DIF and something. In any case, what's the main thing that you do in DIT? In DIT, you start with smaller butterflies and then eventually like start building bigger butterflies. And wait a second. Sorry. You use the bit reversed, what is it called? Sequencing of x sub n values, right? To kind of arrange them so that you get like the correctly ordered values in k of xk, right? So you would go like x sub So for example, if you had like a 4-point signal, it's like x0, x1, x2, x3, x4. Sorry, it's just x3 in fact. So like 0 is 0 0, 1 is 0 1, this is like 1 0, and this is 1 1. Well, bit reverse this thing, just get 0 0, which is actually just 0, and then you get 1 0, which is like 2, and you get 0 1, which is 1, and then 1 1, which is 3. So you would like do something like this: x0, x2, not x1, x2 over there, and then you got x1 and x3. So that's the bit reversed ordering. And then you start like drawing butterfly diagrams. So you start off with the first two, and then like pair the first two, then the next two, and so on. Then the next level you pair the first four, and then so on, like 2 power a pairing. But yeah, so butterfly diagram is something like this, where first you multiply by omega sub 2, because you're dealing with two of these guys. So omega sub 2 is basically like e power minus j. I shouldn't say omega, let's just call it like w sub 2, that's minus j, and then you got 2 pi upon this number, which is 2 over here, and well, actually that's it. Right, so multiply by that over there, similarly multiply by that over there, you have a -1. This is just directly that, and it's like -1 over there. Then next level you do this kind of butterfly shit. Yeah, where over here in these two cases you multiply by omega sub 4 power 0, sorry, capital, so yeah, and over here you multiply by like w power 4 sub 1, but once again like w power 4 is given by the same stuff, but 4 in the denominator over there. Yeah, and then you got like minus, and then over here you just got plus 1 plus 1. Cool. And that's how you get the DFT pretty easily. Yeah, so that's the estimation in time. Just completely reverse this butterfly diagram stuff and like the indexing as well, and then you'll just have, you know, the, what is it called, DDIF thing. Yeah, I guess. Yeah, seems about right. Is this correct? Okay, this is like complicated shit. Oh yeah, okay, so the thing was like over here you just say capital X, capital X, capital X, capital X, and this is like small x, small x, small x, small x. It's not k, it's like 0 1 2, by the way, 0 1 2 3. So even this, like going from right to left, flowing from right to left, you would just obtain the same thing, like it's correct as in. So now these will be in bit reverse order. These are like in normal ordering. Your x of n and x of k are in bit reverse order, and then your butterflies are having the multiplier at the last instead of before them. So just like run a small comparison and see what's going on. So this is how it looks. It's like completely transposed, if that makes sense. I know it's like a bit too small for you to see. In any case, let's move on. That's FFT, not worth my time. This is like the continuous time stuff, which is not there in my course, so I'm not gonna like share it with you on video. But yeah. Oh, so these are like important, but nobody for some reason talks about these guys. So first, a normal band pass filter. How do you do it? Okay, how do you just like, what is it? That's more important. So band pass filter, as the name suggests, is just something that passes frequencies that live in a band with the same amplitude gain. It may or may not give you the same frequency, the same phase change, but if it does, well then good for you. So for example, our, you know, perfect band pass filter would just have one everywhere in that interval, and we know like to implement that you need a bunch of multipliers because it's a sinc function and it's like extending over time. Sorry, yeah, the impulse response will extends over n all the way from negative infinity to infinity. Okay, then you have a digital all pass filter. So an all pass filter is once again something that passes every frequency with the same magnitude of the coefficient that you put in. So like h of z has the same amplitude everywhere. in words, this would something like this. This is equal to, I don't know, 1 for example everywhere. Yeah. And so the way to implement this is, let's just say that you have a pole z naught. I'm actually gonna like close this because I don't want to be seeing it. It's the test, right? So if you have a pole z naught, then just take 1 upon z naught bar as a 0, right? And don't just put like z minus 1 upon z naught bar. No, instead simplify it and then put it. So it's like z naught bar z minus 1. Yeah, that's what you have to be putting there. And so that will have like its magnitude being equal to 1. And no, the phase is not like anything special, it's not a simple expression or whatever, but yeah, this happens. And now you might say, okay, this could potentially give you like a complex rational function. So to just make it actual like rational function with real coefficients, you just multiply by the conjugates. So something like z naught z minus 1, just do that, and then you get like something good out of it. Yeah. Once again, just digital all pass filter. So yeah, it's like z naught is r e power j theta, then this is the kind of expression that you get. Cool. Then you got linear phase FIR filters. So a linear phase filter is something which has a constant group delay, and there are like two very simple ways to build a simple like linear phase FIR filter. One is you start with a symmetric impulse response. So actually like I kind of don't want to go into this, it's a bit too easy for me, but yeah, so I just like say that your impulse response is something like, I don't know, 1 and then 2 and 2 and 1, right? Yeah, then this like the z transform of this impulse response would be something like 1 plus 2z inverse plus 2z power negative 2 plus z power negative 3, right? Well, you pick the centermost value, which in this case would just be 1.5, right? So it's like z power negative 1.5. You like get that out, and now see what you have over there. Just have z power 1.5 plus 2z power 0.5 plus 2z power negative 0.5, and then you got once again the z power minus 1.5. So these two are like conjugates. Easy to see, right? If z, I mean, who am I kidding? Of course these two are conjugates if z is like of magnitude 1, which it will be for a frequency response, right? So in that case, like these two combined will just give us some real number. Similarly, these two combined will just give us some real number. So all in all, the amount of change in like phase that you have, that is just going to come from this. Yeah. And so like we know this is just e power j omega, that's what you put in for z. So this times of negative 1.5, that's like the phase change. Your phase change is just negative 1.5 omega, so then like negative d phi by d omega is just 1.5. It's the group delay, it's constant, so it's a linear phase filter. That's a symmetric impulse response filter. You can do it like for odd length or even length or whatever the hell you want. There's also like the asymmetric impulse response, where instead of these being added up giving like some real numbers, these pairs added up gives us like j times some real number, right? Or mainly like the imaginary part but multiplied by j. So you just have like an extra factor of pi by 2, so you just have like phi is this thing but plus pi by 2 or something like that. And so yeah, that's how you build linear phase FI filters. Then there's like this sampling revisited thing that I've written down, but honestly it's too much for me to explain. Basically I just derived the Nyquist, it's called Nyquist, right? Yeah, it's the Nyquist criteria. I just derived it, you know, and yeah, just look into it if you like get hands on this thing, which I will be sharing in the description in any case. But I'm not gonna go over this because it's not in the exam. So yeah, that's it. Let's see you guys in the next video.